Okay, so we have started our next big unit, which is integration. And so as we look at integrals, remember they are just the opposite of differentiation. And if we're given an integrand of f prime of x, or the integral, then we're going to work backwards to find what f of x was. Okay, so this is going backwards from what we studied in the last unit. So first off, we need to define a few things and some language so that you understand. We're still going to be working with Riemann sum. And Riemann sum, remember, is just the area under the curve. And so as we're working through this, we have to remember that y equals f of x. So the function is continuous. So the function is continuous on a non-negative area of the graph, and that interval falls between a and b. So then the area under the curve of the function from a to b is given by this notation. So this is our new notation, and we're going to go over everything all those symbols mean. And it is a definite integral. So technically there are two kinds of integration that we could do, definite and indefinite. And it's just what it says. If it's a definite integral, it has a specific bound. It's bounded by a vertical line at x equals a and a vertical line at x equals b. And so as we look at the bounded region, we're going to look at the function, the x-axis, and wherever those vertical lines close it in. So we're looking at a definite closed-in shape. So again, two types of differentiation from a to b. One is definite, which is what we're doing today, and two is indefinite, which means it does not have a bound. So the first thing I want to go over symbol-wise is you have this S symbol. I need you to make sure that looks like an S so I can tell that you're integrating. And this S symbol is the verb that means to find the antiderivative. So now that you know what that S means, that means it's the verb to find that anti-differentiation, then we want to look at this whole symbol right here. So you can see there's an A and a B, there's an f of x and a d of x. So let's break down what all of that means. So we have an A here and a B here. So we're talking about the boundaries, okay? So A is the lower bound, or the small one, if you want to think of it that way. And B is the upper bound, or the big one. So we're always integrating from the lower bound or the small boundary to the upper boundary. So we have that. Then the next thing we see in our integral symbol is f of x. And so f of x is what we will think of as the height. And that height is called the integrand. So that's the integrand. Then you see in this notation right here, so we've talked about this part, now you see the dx. And that dx is the variable of integration, so it's the width. And remember that this is on a closed interval, so that width is going to be on a closed interval. And this dx right here is called the variable of integration. So we definitely need to know the height and the width if we're going to determine area. And then because this is actually using my calculus notation, this is going to find the exact area under the curve. Where when we did Riemann sum last time, we used that to approximate. All right, so we're going to have to get comfortable with notation, and we're going to have to get comfortable with deciding, you know, can I use the geometry to figure it out once I know the shape, or do I need to use the calculus to find the exact shape? All right, so that's all of the notation about the symbol. You'll see a lot that happen and used a lot, so you should get pretty comfortable with that. So number one, set up a definite integral. So definite integral means we have boundaries to find the area of the region bounded by this function. at the x-axis, and here's my vertical lines, x equals 0 and x equals 3. We're going to solve our integral using geometric shapes. So let's write down our integral, because we will be expecting to see the integral written on your paper, no matter whether you're using geometry shapes or you're using Riemann's sums. So I'm going vertically from 0 to 3. So between 0 and 3, which one's a small number? Hopefully you can see 0. And which one's the bigger number? So you can see 3. So this are the vertical lines set our boundaries. Then we have the function, which is f of x. And in our case, the function is right here. So we're going to put it in parentheses because it's a string of terms. And so that is our f of x. And then what are we taking the derivative with respect to? We're taking it with respect to x. So this is going to be dx. I'm sorry, the integration with respect to x. All right, so let's give ourselves a rough sketch here. So we're going to have the graph here. And so then we're bounded by the x-axis, which is right here. And we're bounded with 3. So this is going to be 3. And we're bounded with a line that has a slope of 1 and has a y-intercept at 2. So it's going to look something like this. And it's bounded by the axis, the function, the two vertical lines. And I think I pointed to the wrong line, but this is the axis down here. So what I'm actually finding the area of is the space that's in here. And remember, integration area under the curve. All right, so if I can identify some places on this graph, I know that this is at 3. And then if this is my function, I should be able to plug the 3 in here to this equation to figure out my y value. So 3 plus 2 is 5. So this point right here is the point 3, 5. Okay, then the point here, this is at 0. So if I plug the 0 in here, it tells me what that intercept is, which I already knew that, right? So I would have 0, 2. So in this case, we don't really need to use Riemann sum to find the area because we learned how to find the area of a trapezoid a long time ago. All right, so when we find the area of the trapezoid, and remember we did practice the trapezoid rule, so we did review the formula, but in case you forgot, area is going to be 1/2 base 1 plus base 2 times the height. Or you can say the 1/2 the height times base 1 plus base 2. All right, so we don't have to approximate. We can actually plug our information in. We do have the length of the bases. We do have the height. So remember, we're going to think about this as the height, and this is base 1 and base 2. So then we're going to say A equals 1/2. And so I can figure out my height. My height is going to be from here to here, which that is 3. And then I'm going to have my base 1, which is 1, 2 units, plus my base 2, which is over here, which is 3 units. And so I can calculate the area equals, and that's going to be 3 plus 2, which is 5. And then 5 times 3 is going to be, let's see, you know what? So I did catch a little mistake, so I paused the video for a minute and erased that because the distance from here to here is the y value of 5, and I wrote down the x value of 3. So definitely don't make my mistake. All right, so then if we have 2 plus 5, that's 10. And then we have to figure out, like we have to take the half, we have that right there. So take a moment and calculate what the a value is using geometry. So doing the math, 2 plus 5 is 7, 7 times 3 is 21, 21 times half, or half of 21, is approximately 10.5. It didn't give us any units to use here, so we won't have any units in our answer. So that's what one might look like, finding the area under the curve using geometry. So we definitely have definite bounded interval, closed-in shape that we can find the area of. However, a definite integral of a function can represent other fields. So you could be applying it application-wise, something like profit and loss. You could be talking about water consumption. You could be talking about a change in position. You could be talking about like numbers or things when you go into a store and exit a store. And it can be positive or negative values in some of those situations. All right, so the problem with the positive, our definition right now, remember, is we said that we were looking at the area is always going to be positive. So until we get some more formulas in our under our belt here to use, then we're just going to have to do it the old-fashioned way. And we're going to keep the area that's above the curve positive and the area to the bottom, which is going to be negative. So this area right here is what I'm talking about. So I'm using my integral notation right here. And then I am going to look at the area above, and then I'm going to subtract the area below. Okay, so that's my process. So in the linear piecewise function to the right, f has given points and is defined for -2 to 3. And so what is the value of the area under the curve from -2 to 3 of f of x dx? Okay, so let's look at what's going on here. I'm finding the area bounded by the curve, the x-axis. So I am definitely finding this part, and that part is above the x-axis, so it's positive. But I also have a little piece down here that's below the x-axis, and that's going to be negative. So in this case, then we're going to have to split the area under this curve up so that we can use our geometry to find it. So velocity is above and moving to the right, remember, and velocity is below the x-axis and moving to the left when it's negative. And so velocity, it could move to the right or have a positive displacement and then move back to the left some. If I add them together, that would be how far I am displaced from where I started. So as we look at that, we're going to talk about that displacement. So let's start from the beginning. So I need to find the area from -2 to 3. So from -2 all the way over to +3. I'm sorry, -2 to +3. Okay, so take a minute and wrap your mind around that problem. Okay, so as I'm going from here all the way over to 3, that's what this piece of the problem is telling me to do. And it's saying, as we look at our notation, it's bounded from -2 to 3. So -2 to 3, I want f of x, which we said was the integrand, and d of x is the variable of integration. So I need to break this up. I definitely have a triangle right here, and I have a trapezoid down here. So I'm going to break that up, and I'm going to write my integral symbol here to represent my first shape, which is a triangle, which is going to go from -2 to, it looks like 1.5, so 3/2 of f of x dx. Then I'm going to add to that an integral then that's going to start at 3/2 and it's going to go to 3. So remember, small bound to big bound, small bound to big bound. It is still in the function f of x, and the variable of integration is dx. So what I did was I split this up into two geometric shapes, of which I should be able to find the area. So that's the process. Remember that a triangle is 1/2 base times height, and a trapezoid is 1/2 times the height times base 1 plus base 2. The thing we have to remember about right here, though, is all of this is below the line, so that's negative, and everything over here is above the line, so that's positive. All right, so as we typically do, once we take the integral, then we can get rid of the integral symbol. And so we're going to solve this using geometry. So we have the triangle plus the trapezoid. All right, so let's find the area of the triangle first. So then I'm going to go 1/2. And so my base is going to go from here to here, which is 7/2. And then my height is going to go from here to here, which is 3. And then I'm going to add that to what I get finding the integral here. But remember that it's actually negative. So as I am countering this, I can say plus a negative, or I can just change this and say a subtraction because it's negative. So you can have the double sign, or you can just say minus. So the area of a trapezoid is 1/2, and then the height of the trapezoid is right here. That's 1. And then base 1 is 1 unit. Base 2 is 1.5. So I have 1 plus 1.5. Okay, so go ahead and pause your video and finish your calculation out. Okay, so 1/2 times 7/2 times 3 gave me 21/4. And then 1 or 2/2 plus 3/2 gives me 5/2 times the negative 1/2 gives me negative 5/4. 21 minus 5 gives me a fraction that simplifies to 4. So that's how I would do it, finding and using the geometry. So as we've talked about before, don't forget, as we start hearing the words velocity and stuff used again, from, adding on to previous lessons, that when you're finding the velocity, that's the first derivative. So just don't lose sight of that. I think I'm going to come up here and write that down so we have it in our notes. Velocity is the first derivative. And we went over that when we talked about PVA in the last unit. Okay, so now we're going to look at a table, because remember, we have to be able to do things in the graph and we have to be able to do things in the table. So the table here, if I'm looking right here, is velocity. And remember that velocity is the first derivative, okay? So as we look at the problem, we are going to, I kind of ended up with the problem itself on my second page here, so let me pull that up so we can read it. A rocket has a positive velocity, and the table of values that we had from over here goes with this problem. Okay, so a rocket has a positive velocity after being launched upward from the ground. The velocity of the rocket is recorded for several values of t over the interval 0 to 80. Notice it includes 0 and includes 80. And the unit is seconds, as shown in the table from the previous page. Yours is just right above, but I spread it out and realized I didn't get the table there. Sorry about that. The height of the rocket, so the height of the rocket is 140 feet at 10 seconds. So that's the information from the problem. And I'm going to kind of be flipping back and forth so we can look at the table as well. All right, so the first thing in part A says to estimate the acceleration of the rocket at t equals 45 seconds. Show the computations that lead to your answer and indicate unit of measure. So in this one, not only do we have to have the information and the work, we also need to have the units at the end. So as we're looking at on the graph where we're trying to calculate, we can see that we don't have 45, but we can go from 40 to 50 and fit in our 45 right there. So that's what we're using in this first problem. So as we talk about acceleration, remember that x prime at t equals v of t. And in our case, I'm going to look at my values. So x is the position, then the derivative of the position is velocity, which was given. And then we do have an initial condition. So right over here in this part, the height of the rocket is 40. That's an initial condition. And as we're looking at the value here for part 3A, we're going to be estimating acceleration. So the key there is estimating the acceleration. So a couple of reminders here, and actually I think I'm going to move this up a little bit so I have space to work if you don't mind. I'm going to move this up here and remind us that x prime at t equals v of t. And so if I have an initial condition of 10 seconds and the rocket's 140 feet, then I also know that x of 10 equals 140 feet. So that comes out of that. So x is the position of the derivative of position and the velocity which was given. Okay, so part A, so we're going to estimate the acceleration of the rocket at t equals 45 seconds, show the computations that lead to my answer. Okay, so if I'm looking at that estimating acceleration of the rocket at t equals 45 seconds, then if I have velocity and I want acceleration, what do? I take the derivative. So it's actually asking me for v prime of 45. All right, so if we want to find v prime of 45, I have a little bit of a problem, again, because 45 isn't actually in my table, but I can use my A-rock to approximate. All right, so then I'm going to set up this as v prime of 45, and then I'm going to go to my table, and I'm going to get v of 50 minus v of 40 all over 50 minus 40. And so then I can go into my values and get those values from the table. So you have your table there. Since I'm flipping back and forth, I'm going to pause for a minute so I can get those values and not make you seasick hopping back and forth. Okay, so as we got our values, v of 50 was 40, v of 40 was 35 over 50 minus 40. So 40 minus 35 gave me 5 on top, 50 minus 40 on bottom gave me 10. The fraction 5/10 simplifies to 1/2. So now I need to deal with my units. So on the top, the value on top represents feet per second. The value on bottom represents seconds, so it's feet per second squared. All right, moving on to part B. So in part B, we're back to Riemann sum. So it tells us the midpoint Riemann sum. It wants 3 subintervals, equal length, and we're using this integral statement to approximate it going from the velocity from 10 to 70. So remember finding the area under the curve, and we have some bounds to this. So let's go ahead and set up our table. So we're going to have intervals, and you have to figure out what those 3 intervals is going to be. And so I've got to go from 10 to 70. So I'm going to go from 10 to 30, and then I'm going to go from 30 to 50, and then I'm going to go from 50 to 70. Okay, so what are the widths of all of these intervals going to be? 20, 20, and 20. And then I'm calculating the height. So as I calculate v of 20, it's 22. As I calculate v of 40, it would be 35. So remember, midpoint means in the middle. So the height for my problem then is going to be v of halfway between 10 and 30 is 20. And then I can go to my table at 20 and see that it equals 32. And then halfway between 30 and 50 is 40. So I can do v of 40 and then go to my table and find v of 40 is 35. Then halfway between 50 and 70, so as I'm doing the halfway between there, and then I'm going to go to my table and figure out what that is. So go ahead and calculate that now. Okay, so hopefully you have your table complete. So now we're going to use our calculus notation this time instead of saying just the accumulation of the area. So the accumulation of my area is they're giving it to me right here. So I'm going to say the integral from 10 to 70 of v of t dx is going to be, and then I can do my midpoint summation. So it has a common width, so I can pull that out. And then I'm going to have v of 20 plus v of 40 plus v of 60. And then I can go through my integral from 10 to 70, v of t dx. I'm going to get 20, and then remember I'm adding these together. So 30, 60, 70, 80, 90, 100, and 9, 10, 11 times 20. All right, so as I'm accumulating my area here, I'm using my symbols correctly. Make sure that I can determine that that is an S, the integral symbol. Sometimes students get really lackadaisical here. If I can't tell it's an integral, I can't give you credit for that. So then we're going to add all the areas up. So 32 plus 35 plus 44 gives me 101 times the 20 that's there. So it's approximately 2,020 feet. Why is it feet? Because what are we trying to do here, right? We're looking at those units. And so if we're going backwards, then we're talking about a distance. All right. So let's move on to part C. Part C is using correct units, explain the meaning of 10 to 70 v of t dt in terms of the rocket's flight. On our test, on an FRQ, it will probably be a tabular data question. It usually almost always gives you a velocity or a derivative and expects you to predict the derivative of that, which kind of represents the second derivative. Then it asks you to approximate or predict the antiderivative. And it kind of follows this pattern. So right here, as we're looking about explaining in terms of the context, we have to make sure that we understand what this means. So finding the area, or in terms of the rocket's flight, then I'm going to say the displacement of the rocket. And what are the units? In feet from our boundaries, 10 to 70 seconds. So we're definitely going to be practicing using the correct units, explain the meaning of that, and notice it says in terms of the rocket's flight. So we have to be sure that our explanation does those things. All right, part D. What is the approximate height of the rocket after traveling for 70 seconds? So as I'm looking at this, I want to pay attention to this wording, after traveling for 70 seconds. So what's the approximate height? So as we're doing that, we're going to use our notation, and we're going to keep that in mind. That means we have an initial condition. So as we see this after traveling, that means we're dealing with an initial condition. And that initial condition we got from the original problem. So remember up here when we calculated, and I told you to mark this as an initial condition so that you would not forget it was there. So that's what we're doing right now. We're using this initial condition that we calculated of 140 feet. So we're going to write down the initial condition first. So that's 140, and that's the initial condition. And I am expecting that to come first, not as an afterthought. All right. Initial condition means it's happening before anything else. And then we're going to add the area under the curve that we just found. So using our calculus notation, we're going to go from 10 to 70 of v of t dt. And so then as we calculate that, make sure that we're kind of figuring this whole thing out, right? So here was 140, and what did we figure out this area was from part B? It was 220. So if I add 140 to 220, then I would have the total of 2160 or 2,160, and the units are F of t. So we want to make sure that we're showing this statement using the calculus. So that's the initial condition plus the integral from 10 to 70 of v of t dt. We calculated this in the last part, so that's our 2020 feet plus another 140 feet. So if this is feet and this is feet, then we should have a unit of feet at the end. Okay, so right now go ahead and get out your green cardstock, and if you want to have these handy to look at, that's fine, but we're going to add all of these rules to our cardstock, and since we're dealing with properties of definite integrals, we're going to be looking at this top section. All right, so these are some rules to learn. So in the first one, notice that A and the B boundary are the same thing, so they have the same boundary. And when we're learning properties here to help us simplify those kind of calculations we were just talking about. So when they have the same boundary, then there is 0 of that area. Number 2, notice here it says B then A. So we know from our definition it has to go A to B. So when we want to flip these boundaries, we use a negative sign, and then we have the boundary from A to B, f of x dx. Okay, so this is when we want to flip the boundaries. All right, and so then the next one is the integration from A to B. So this time the boundaries are correct. We have a constant value right here. And so when we have that constant value, we can actually pull it out in front. So I can say the constant and then do my integration from A to B of f of x dx. So this one has a constant in it. All right, and so this one we get down here and we're talking about sum and difference of two different functions. So we can split this up and take the integral of the first function and the integral of the second function of the same boundaries. So I can split this up and say I'm going from A to B of f of x dx. Then I'm going to add or subtract same boundaries from A to B, but this time it's going to be g of x dx. Okay, make sure you get the dx on both of these because we need that variable of integration on both of the two things that we're taking the integrals of. All right, so the next one is here. And so we have the integral from A to C of this f of x dx, and then from C to B of f of x dx. So what this means is that I can actually just find the integral from A to B of f of x dx. Okay, so that piece right here in the middle, since they're both integrals, or this one is going to end at C and this one's going to begin at C. And finally, when we have dx, so notice that there is no function in front of dx, there is no constant in front of dx, it's just 1. And so when that is just 1, then we can go from A to B and we can find that area by saying B minus A. So if we look at a kind of a graph of what's going on here, so we have this function and we have A here and we have B here. And it is a height of 1 unit here. So that's going up to 1 unit of 1. I don't have my axis marked. So what we're finding is this part right here, and we can do that by just simply subtracting b minus a, and that will give us that interval. Okay, so keep your cardstock handy as we work through these problems so that you can use these rules and practice these rules in the next part. All right, so these are all on our cardstock. That's what we just updated. So we're going to go down to problem 4. So notice I'm going from 1 to 3 of x squared dx, and that equals 26 over 3. And then I'm going from 1 to 3 of x dx, and that's going to equal 4. And I'm going from 1 to 3 of dx equals 2. And I'm going to use this information to evaluate these next problems, that and the properties that we just talked about. All right. So here is 1 to 3 of 3 x squared dx. So which rule does that look like? That looks like number 3 right here, where we have a constant. So we're going to write the constant outside. We're going to calculate the area from 1 to 3 of x squared dx. Don't forget your dx there. And then when we do the area for that, we can calculate the numbers. So we're going to end up with a 3 times whatever we get from the area here. So pause your video and see if you can figure out what the area is between 1 and 3 at x squared. Okay, so as we look at this now that we have it written out, we pulled out that constant. Notice that this is a fact that's given here. So the value of the integral from 1 to 3 of x squared dx is 26/3. So then as we have 3 over 1 times 26 over 3, which is given, then that lets me find the final area to be 26 because these 3's are going to cancel. Okay? So let's move on to B, which goes from 3 to 1. So hopefully we see we have 2 rules here. We have the rule that has a constant, and we have the rule that deals with when our boundaries are backwards, because 3 is the bigger number than 1. So this boundary doesn't need to go from 3 to 1. It needs to go from 1 to 3. And our rule that lets us change the boundaries is rule number 2, which means that we have a negative that comes out in front. So the first thing I'm going to do is bring out my 4, and then I'm going to change my boundary so that becomes negative, and now I'm going from 1 to 3, and I brought the 4 out, so what's left inside is x dx. Okay, so I can see from 1 to 3, x dx equals 4, so I'm going to have -4, and then I'm going to have the value in here of 4. So -4 times 4. And so that means the area for this problem is what? -16. All right, so again, practicing using the rules, and then also we're given information. So we're not having to find the area right now. We're given facts to use to be able to do that. All right. So this one, excuse me, this is a sum and difference. The boundaries are in the right order. There's no constant to bring out. So I'm going to split that up into my 2 functions. So remember that when we do the sum and difference rule, we're going to break them into 2 separate integrals with the boundaries and then plus or minus in between. All right. So then we're going to go from 1 to 3 of 3x, and remember you need to bring the dx with each part as you expand it and apply the rule, minus the integral from 1 to 3, and the second part right here, which is 5 dx. Okay, so you probably saw when you were working this problem that we had constants in here. So you could have went ahead and started out by bringing the 3 outside and going from 1 to 3, and then we would have x dx minus, and bring the 5 out, and then we would go from 1 to 3, and since the 5 is outside, then I have dx right here. So keeping in mind that I did it in 2 steps, and maybe you saw that and did it all in 1 step, that would work. It might be quicker if you knew like the full shape, that you could maybe do geometry, but definitely you can get to it without needing to do that. So then we want to find x dx, and then we want to find when we go from 1 to 3 dx. So go ahead and apply your rules and see what you can get for this part of it, and then we'll compare final answers. So pause your video. All right, so hopefully you recognize that this is x dx from 1 to 3, so that equals 4. So you have the constant in front times 4. And then 1 to 3 dx is this one right here, which equals 2. So you have the constant in front of 5 times 2. So 3 times 4 is 12 minus 10, which gives us an answer of 2. And that's what this integral up here equals, is 2. Great job. Moving on to problem 5. Okay, so on problem 5, they're giving you some more facts to deal with. And notice here the boundaries are different. So the boundaries here are going from 0 to 3, and the boundary here is going from 3 to 6. So keep that in mind. So what I want you to do now is try your hand at these rules. I'm going to ask you to go ahead and pause and evaluate using the properties from your cardstock and the facts that you're given in the problem. Be sure that you're using good notation and set up your interval with your notation before you actually solve the problem. It is not a suggestion, it is a requirement. So go ahead and pause that video and work on A through D, and then we will come back and compare. Okay, so let's look and see how you did. So these are the two facts that we're using. So in this first one, from 0 to 6, I had to split that up because this went from 0 to 3 and this went from 3 to 6. It didn't go from 0 to 6. So then I have 0 to 3 of f of x dx for this part, and I have 3 to 6 f of x dx for this part. Then that's looking at property 5. So I can go ahead and pull the values down. So this is equivalent to 4, and this is equivalent to -1. So 4 plus -1 is 3, which means the integral from 0 to 5, nope, yep, 6, sorry, 0 to 6 of f of x equals 3. On B, I'm using the rule that lets me switch the boundaries, so that's property number 2. So now I'm going from 3 to 6 of f of x dx because the boundaries flipped. And so then I have a -1 from the outside, and the fact that I'm using from 3 to 6 is this one, which is -1. So -1 times -1 is +1, or the area for this integral is 1. This one goes from 3 to 3. Those are the same boundaries, so that's property 1. And when it starts and stops at the same point on those boundaries, then the area or the integral equals 0. And finally, the part D goes from 3 to 6, and it is a sum and difference in here, plus it also has a constant rule right there. So I split it up because I don't have, I have from 3 to 6 here, but then I need to look at both of these. So first thing I did was split this up. So I pulled the -5 out, went from 3 to 6 of f of x dx inside. Remember, you have to have the dx there to get credit. And then the second function was 4. So I went and pulled the 4 out because that's a constant. Now it's going to go from 3 to 6 of just dx. So I used property 3 and 4. So now I can do -5, and then the integral from 3 to 6 is right here is -1. And then I can do 4 times the integral from 3 to 6 of dx is going to be 3. And then -5 times -1 is 5. 4 times 3 is 12. 5 times 12 is 17. So that's what the integral equals. Okay, so the last two problems we're definitely using the properties, and we are going to use the properties this time, but instead of having the two equations to give us the information we need, we're going to be using the graph to give us the information we need. So the first thing we typically do in a problem like this is break the graph up into smaller pieces. So anything, remember, below the line is negative area, anything above the line is positive area. And if I'm doing total distance, that's the absolute value of all the areas. So I'm going to come in here and break this up. And so I'm going to break it up at 3. And I think I'll do it at 4. And then I have a little triangle. So let me straighten my line up here. So I have a triangle below. I have a triangle right here. I have a rectangle. I have a triangle. Then I can find, this is a good distance here. So I can find the area of this triangle. And then I have my final little area right here. So pause your video and calculate the area of those shapes. Okay, so hopefully we found the area, and remember anything down here is negative, so this is a -1/2 for this little triangle, this is a -4 for this triangle, this is a +1/2 for this triangle, a 2 for this triangle, a 2 for this triangle, and a 2 for the rectangle in the middle. So as we use our graph here and these areas that we've calculated, we're still going to write our integral statements, but then we're going to use the actual area of the graph to find the area here. So for instance, on A, it goes from 0 to 1 and it's negative. So we know we can pull the negative out in front, and we'll have negative from 0 to 1 because we can pull out that constant of f of x dx. So then if I go to my graph and I go from 0 to 1, I find that that is a negative area of 1/2 because it's below the line. And then if I take the negative 1 that's right here and I multiply it by that negative 1/2 from the area on my graph, then I'm going to find that it's negative 1 times 1/2, so it's positive 1/2. And what I just found was the area of that curve, which is from this. So going from 0 to 1, pulling out that negative and being able to determine that. So what property do you see here? I could pull the 3 out in front. The boundaries are in the right order. So then I could go to my graph and look from 3 to 4, and the area is 2 times the 3 that I pulled out. So as you write that statement, then you're going to pull out the 3, and it's going to go from 3 to 4, and then it's going to be f of x dx, and we can't remember to have that dx in there. And now that I've done that, I'm going to go to my graph and I'm going to find this area under the curve from 3 to 4, which is this rectangle right here, which is 2. So I'm going to have 3 times 2, which makes the area here 6, and the area of this integral right here is 6. All right, so everybody got the idea? So you're using the graph here. Notice you're going to have to separate. Boundaries are okay here, boundaries are okay here, boundaries are okay here. This is the absolute value. So the absolute value means that we just are going to kind of pretend like I could flip this up here and now make the graph above there. I could put my triangle up here and make this go to the top. And so we're just adding the total areas across. So go ahead and pause your video and practice finding the area with the graph, and we'll come back and compare answers. Okay, so I'm setting up my boundaries, and then I'm going to do the calculation, find the part in the graph that I need to find. So when I go through this, I'm kind of breaking all of this up. So I'm going from 0 to 1. I brought the negative out. From 0 to 1 on the graph is negative 1/2. So negative 1 times negative 1/2 is positive 1/2. And then I went to the next one and broke it up again from 3 to 4, brought out the constant on the graph. This is 2. 3 times the constant times the 2 is 6, so the area is 6. Here I had to split this up into multiple intervals so I could use the areas I calculated on the graph. So I went from 0 to 1 of f of x dx, 1 to 6 of f of x dx, and 6 to 7 of f of x dx, making sure the dx is in all 3 integrals. So on the graph, this area from 0 to 1 is negative 1/2. This area from 1 to 6 is positive 6. This area from 6 to 7 is negative 1/2. So negative 1/2 plus 6 minus 1/2 gives me 5 for that integral. Down here I have the plus or minus rule, so I have to split this up. So I did from 5 to 11 of f of x dx, plus brought the constant of 2 out from 5 to 11 dx. So 5 to 11 f of x dx on the graph is negative 3. Here, remember rule 6 says if it's just dx, so it's 1 dx, and all I have to do is subtract the boundaries. So 11 minus 5 is 6 times the 2 that I brought outside, so 2 times 6 is 12. 12 minus 3 gives me an integral of 9. On E, I'm going from 0 to 11, so from 0 to 11, and I'm just adding and subtracting the areas, well actually adding the areas, but just keeping in mind that some of the areas are negative. So negative 1/2 plus 2 plus 2 plus 2, negative 4 plus this positive 1/2 right here, and we add all that up, we get 2. And finally, the absolute value means that all of the stuff that's below, it's like it reflected on top. So I move this triangle right here so I could see it, and I move this triangle that's below up here so I could see it. And then all I'm really doing is adding all of the areas up. So now this triangle is above, so it's positive plus 2 plus 2 plus 2. And this triangle is above, so now it's positive 4 plus the positive 1/2. So when I add all that stuff up, I get 11. All right, so one last problem and we're finished with today's notes. So go ahead and do what we've been doing. And I guess when I'm talking about what's happening in this problem, we're doing the different segments, we're using the graph. So keep that in mind. And if you're talking about the total distance, like in this last one, basically 2 to the right of where I started, but it traveled 11 total distance. So just kind of throwing that out there. So go ahead, do these last two, and use this graph here to figure out the values from these problems. So basically, the graph here, I'll give you a little context. So as I'm looking at this right here, I see my boundary goes from 0 to x of f of t dt. So g is the antiderivative of f, then f is the derivative of g. So if g is the antiderivative of f, then f is the derivative of g. So they kind of undo each other. And so remember, the integral means area under the curve. So I'm going to come over here and split this up right here. And I'm looking for g of 1 and g of negative 2. Okay, so when we're looking at this, this means g is the antiderivative of f, then f is the antiderivative of g. It's got our symbol there. It's going 0 to x. X is a variable. So when I'm asked to find g of 1, that means that x now becomes a 1. So I'm looking at my graph from 0 to 1 of f of t dt, because this is a graph of f, and so on this graph from 0 to 1, this is this little triangle right here, and that is 1/2 because the height is 2, the distance here is 1, 2 times 1 is 2, and half of that is 1. So g of 1 equals this area under the curve of 1. So what does that mean? That means on the g graph, the antiderivative graph of f has the point at 1, 1. So remember that we can sketch a graph, we can find the derivative of the graph, and then we can use that and go back into the original equation. We can look at increasing, decreasing, concave up, concave down. But the problem is we didn't know where. This is how we find the where. Okay, so make sure you're using your notation here correctly. You get that dt on here, right, when you're using this part, and then use your graph for that. So go ahead and pause your video one last time and try your hand at calculating g of negative 2, and then we'll come back and compare. Okay, let's see how you did. You should have got negative 17 halves. So we broke the interval up. So when we put the 2 up here, so that's negative 2. Technically, I don't mean that. We didn't break it up. We just applied the negative 2 here, but we can tell 0 to negative 2 is reversing the boundaries because this is not the bigger number. 0 is bigger than negative 2. So I pull out a negative so I can reverse the boundaries, and then I need to find the area under the curve from negative 2 to 0 of f of t dt. So at g of 2, this negative on that side is there, and so under the curve, that's going from here to 0, and so this part is 7/2, so that's 1/2 base 1 plus base 2 times the height, and this triangle is 5. So I need to add this area together from negative 2 to 0, so 5 plus 7/2. So 5 times 2 is 10 halves, 10 halves plus 7 halves is 17 halves, multiply by the negative outside, and you get negative 17 halves. Be very careful when you're doing this. Remember that each step with that equal sign should have something on both sides. You're not solving this equation. This is the notation that shows what you're doing. We don't ever leave open equal signs because then we're saying 0 equals all of that, and that's definitely not the case. So again, splitting up the areas onto the graph to calculate what we needed using our current notation and realizing that if this is g of 1, well, this x here is the same thing as this x there, so we should be able to calculate that value. All right, guys, that wraps up today's lesson on definite intervals. Be sure you're practicing your daily practice because we will be looking at indefinite intervals, and we're going to make sure you've got the basics from this lesson before we tackle what do we do when there's not a definite boundary. All right, thanks, guys. Bye.